Hey, welcome to the Explainer. Today, we're diving into a really powerful upgrade to standard logic called hybrid logic. And we're going to focus on a crucial question. Once you have this more powerful logic, how do you actually go about building formal, rock-solid proofs with it? Okay, let's just jump right in. This might look like a simple question, but for ordinary logic, it's a lot trickier than you think. I mean, how do you talk about one single, unique event? Standard logic is great with general statements, but it really struggles with this kind of pinpoint accuracy. And that exact problem is what sets the stage for a really clever solution. So here's what we've got on tap. We're going to start by seeing what standard logic is missing. Then we'll introduce the new tools that fix it. And from there, we'll see how those tools completely revolutionize two major ways of building proofs: axioms and tableaus. Right, so before we can really appreciate the solution that hybrid logic offers, we first need to get a good handle on the problem it was designed to solve. And that is the challenge of being specific. This slide just nails the problem, right? Standard modal logic is totally fine with a statement like, "it is raining." I mean, its truth can change depending on the time or the possible world you're in, but it completely hits a wall with the statement on the right, something that's true at one and only one specific moment. It just can't express it. So, the bottom line is, ordinary logic can talk about possible worlds in general, but it can't actually point to one and say, "I mean that one right there." And that's a huge expressive limitation. So, how do we fix this? Well, the fix is what we call hybridization, and it's the core innovation of hybrid logic. It gives us a simple but incredibly powerful new toolkit, the ability to give names to specific moments or worlds right inside our logical formulas. First up in this new toolkit, we have nominals. Honestly, the easiest way to think about them is as literal name tags. You can take a symbol, like A or B, and just stick it on a specific point in time or a single possible world. It becomes its unique identifier. The second tool is the satisfaction operator, which we write with the @ sign. And this thing is awesome. It's basically a logical teleporter. It lets you instantly jump to any world that has a name tag and check if a statement is true there, no matter where your starting point was. And here's how they work together beautifully. You get a formula like this, @AP. It uses that teleporter, the @ sign, to jump to the world we've named A, and from there, it just checks if P is true. And just like that, we have pinpoint accuracy. Okay, so now that we have these new toys, the ability to name and jump to specific worlds, how do we actually prove things with them? Let's start with axioms, which are kind of like the fundamental, self-evident building blocks of a logical system. Because we can name worlds, for the first time we can write down some super obvious common sense rules about identity that were just impossible to say before. Things like, a world is identical to itself. Or if A is the same as B, then B is the same as A. Basic stuff about identity that we can now express right inside the logic. Disability leads to a really important idea, something called pure formulas. Now, these are special sentences that only use our new name tags, the nominals. The key thing to remember is they don't care about what's happening in the worlds, like if it's raining or not. They're all about the map of the worlds itself, how they're all connected. And that's where the magic really happens. What this basically says is that we can create one core set of rules, one general-purpose axiom system. And then, if we want to work with a specific kind of structure, say one where time can't go backwards, we just bolt on the pure formulas for that structure as extra axioms. And you guys, this is a total game changer. It means we don't have to invent a whole new proof system from scratch for every little variation in logic. We can just plug and play the right pure axioms. It's an incredibly uniform and modular way of doing things. All right, so that's axioms. But what about another really popular way of proving things? Let's talk about tableaus. It's a totally different approach to finding truth, and it's another area where hybrid logic gives us a massive upgrade. The whole idea behind a tableau is to work backwards. It's kind of like playing a game of logical Sudoku. You start by assuming a formula could be true, and you systematically break it down into smaller and smaller pieces. If every single possible path you explore leads to an impossible contradiction, like a world where P has to be both true and false at the same time, well then you've proven the original formula must be a logical truth. Yeah, so this table really breaks it down. Axiomatic systems are all about building up from a foundation of basic truths. Tableaus work backwards. They're like detectives trying to find a flaw in a story. They serve different purposes, but Tableau are especially great for automated reasoning, for getting computers to do the work.
And the process is super methodical, which is why computers love it. You start with your formula, you apply your decomposition rules, and here's that hybrid secret sauce again. You can introduce those pure formulas as facts about the structure you're working in. Then you just hunt for a contradiction, a clash on any branch. If you find clashes on all of them, you're done.
And does this sound familiar? We see that same awesome advantage pop up again, uniformity. It's that same plug-and-play idea. We can build one general tableau system and then customize it for all sorts of different logics just by adding the right pure formulas. It makes hybrid tableaus incredibly flexible and way more powerful. Okay, so we've got these really slick, really flexible proof systems for both axioms and tableaus. But, so what? Why does any of this actually matter outside of a logic classroom? Well, the payoff is huge. First, you just get way more expressive power. You can describe things ordinary logic can't touch. You get these awesome uniform proof systems we've been talking about, and it all leads to better algorithms and has real-world uses in stuff like AI, advanced database queries, and even verifying that computer programs work the way they're supposed to. But honestly, this might be the most mind-blowing part. P-space is just a fancy computer science term for how hard a problem is for a computer to solve. And even with all this new power, this extra ability to name things and jump around, the basic hybrid system doesn't get any harder to solve. It's in the exact same complexity class as the old, weaker logic. It's like getting a supercar engine that uses the same amount of gas as a sedan. It's just better. So, it turns out a really simple, elegant idea, just giving things names, can totally revolutionize a complex system, streamlining how we prove things and unlocking all sorts of new potential. Which leaves you with a pretty fascinating question to think about. Thanks for watching.